Hi everybody, I hope you're doing well. In this lecture we will discuss the Fermi gas, which is one of the most fundamental theories in condensed matter physics. It was introduced by Enrico Fermi around 1926, and it generalized the concept of an ideal gas to fermionic matter, which means obeying the Pauli exclusion principle. So Fermi did that. He considered the Pauli exclusion for an ideal gas of free particles. In this case, we nowadays call them fermions. So it's a gas of free fermions, or at least weakly interacting fermions. Interactions can be dealt with as, as a perturbation in the next order correction. Okay, so at first you consider a gas of free particles or free fermions. The applications of the Fermi gas. Well, there are applications for the free electron gas in a metal. We will focus ourselves here in this problem, and semiconductors, where you can treat the electrons and the holes as a Fermi gas. Okay, and it's very good approximation. The free electron gas is very good approximation for the alkali metals. There are some corrections to be done, all right, because there are interactions between the electrons. But as a first approximation, it's a good approximation for alkali metals mainly, but in general for metals. For neutron stars, a Fermi gas has an intrinsic pressure even at zero temperature, the absolute zero temperature, and this pressure of a Fermi gas helps to stabilize the star, preventing its collapse. Okay, because there are pressure forces acting contrary to the gravitational pull, and it prevents a collapse. The atomic uh, the atomic nucleus, which is composed of protons and neutrons, and a model, very simplistic model, can use a Fermi gas to deal with the atomic subatomic particles inside the nucleus. Okay, and of course there are the ultra cold atomic systems, which can be considered as first approximation as a gas for fermionic atoms. Okay, but we will be more interested in this case. Okay, so what is the model for a Fermi gas? There are two possibilities: a relativistic Fermi gas or a non-relativistic Fermi gas. Our main interest here is in non-relativistic Fermi gas. And in this case, electron gas. Okay, so non-relativistic electron gas. This is our main interest here. So the Hamiltonian of our problem corresponds to a summation over all the wave vectors and spins of the electrons, the energies which can be corrected by spin, and the number operator here. So it is already in second quantized form. Okay, this is a second quantized form. The total number operator here, the total number is just the summation over C dagger C for K and sigma. Okay, so this is the Hamiltonian, this is the number operator. And for the energy dispersion relation, so dispersion it is a parabolic for non-relativistic. Parabolic form. Okay, so you have to consider the energies in the following form: h bar squared divided by twice an effective mass. I will discuss it in in, in brief. Okay, so this is an effective mass times k squared here, which is the modulus of the wave vector. Remember, momentum is h bar k, and you can add corrections for spin, but for electrons, the down spin in the presence of a magnetic field is a more favorable configuration. Of course, you can also define a magnetization which is proportional to, you can put this way, a magnetization around the z-axis. It is an operator. It corresponds to the operator for n up spins minus n down. Magnetization for electrons is the reversed order. Okay, times the Bohr magneton here divided by the volume of your sample. Okay, so this is the magnetization operator. This is the energy spectrum. And of course, you can calculate the K here. K is equal to 2 times the effective mass divided by h bar squared, the energy given that K, minus the Bohr magneton sigma times B. B is a magnetic field, a static or DC magnetic field. Applied in Z direction. This is the modulus, of course, the amplitude, the modulus of the magnetic field applied in Z direction. Okay, positive Z direction. This is modulus of the magnetic field. This is the spin correction. There are orbital corrections due to magnetic fields. We will talk about that later. All right, so this is the main picture of our model. This is the Hamiltonian. This is number of particles, magnetization. You can calculate also other properties, physical properties of your problem. All right. So now let me just discuss a few issues very relevant for the moment. So effective mass. I will not try to introduce any formula here, okay? But the effective mass of the electron, it just corresponds to the effect. It's a correction to the electron mass. It's a correction to the electron mass due to electron interacting with the positive background. So due to interactions of the electron with positively charged background provided by the ionic lattice. You have a lattice with positive ions, okay? And electrons interact here with these ions, but a way to not take into not include this into your problem is to replace the whole scenario by an effective mass. So another way to put that is the effective mass is a way to take into consideration the electron interactions with the background, with the lattice. For crystalline solids, the distances between the atoms are very well defined. It must be a crystalline lattice. Suppose there are all identical distances, so suppose A. And in this case, this positive background is taken into account by replacing the Coulombic interactions, which is attractive, by an effective value of the mass. And there are another issue here, which is electron-electron interactions. Okay, the electron-electron interactions, because one electron here, it sees another electron, perhaps, and they repel each other. They have the same charge, but you can neglect as a first at the most important order, the lowest order, neglected in a first approximation. And why you can do that? Because Coulomb interactions are screened by the positive background. So there are two effects of the background. One is to correct the electronic mass, and the second is to screen the Coulomb potential. Okay, so the Coulomb potential would be, the energy would be of the form U equals to E squared divided by 4 pi the epsilon of this medium, the electric permittivity of this medium. Usually you could put a vacuum value here, but the distance of two electrons, R1 and R2, no matter the order here because in modulus, times the exponential of minus alpha, the modulus of R1 minus R2. Let me put it in this order. And this alpha is too large, and the Coulomb interaction falls very quickly. So the possibility of interactions is very attenuated by this factor. Just remember that the Coulomb interaction in momentum space, it will be on the order of the charge squared divided by the momentum transfer between the electrons, which we represent by the modulus of some vector k squared, plus that alpha squared. And this alpha is large. The Coulomb interactions fall off very quickly. So this alpha is huge, and this interaction is tending to zero. Okay, it's a very good first order approximation. Neglect electron-electron interactions. Okay, so let me summarize. Effective mass takes into account the positive background, which corrects the mass in the medium for the electron gas. And electron-electron interactions can be neglected due to the screening of the electronic charge by the positive background. These are two effects of the lattice to the electron gas. Okay. Now we can calculate many things here. We can calculate the number of electrons Okay, Fermi level. What we can calculate, we can find relations between the Fermi level and the density of the gas. Then relation to density of the Fermi gas. We want to calculate the total energy of the system. We want to calculate specific heat, or prior to that, the chemical potential, specific heat capacity, okay? But for short, specific heat, and pressure, the gas pressure, electronic properties, magnetization, okay, using the approximation of a gas, right? So let us start, consider three dimensions, 3D, okay? You can do it for a one-dimensional gas or for a two-dimensional gas, but the most relevant aspect here for the general situation is a three-dimensional world. Okay, so we are considering a three-dimensional problem here. And of course, we will do that using Fermi Dirac statistics. So the first aspect is to calculate a relation between the Fermi level at temperature equal to 0. Just remember, the Fermi Dirac with respect to energy is the following: 1 till you reach the Fermi energy, Fermi level, and 0 otherwise. Okay, the temperature produces the following: the smearing of the Fermi Dirac. So this is for temperature distinct from 0, not equal to 0, and this is for temperature equal to 0. This is the Fermi Dirac distribution, which related to the chemical potential is written the following way: e to the beta energy minus chemical potential plus 1. Chemical potential at 0 temperature is equal to the Fermi level. Okay, so and beta is the reciprocal of the temperature, just for you to remember that fact. Okay, these are important aspects of the Fermi Dirac distribution. So at temperature equal to 0, the Fermi Dirac distribution is step-like, and we will take that into consideration. Okay, now let us calculate the total number of particles in the system, considering the number operator. So the number operator in the average, it is equal to a summation over k and over the spins, the average number. So also consider at t equal to 0 a magnetic field equal to 0. So there are no magnetic fields, there are no spin corrections, there is a degeneracy of spins. The number of the factor of degeneracy is 2, because electrons are spin half particles. Okay, so the total number here, we already calculated that, is just corresponding to the Fermi Dirac function or distribution. So we need to calculate the following: the Fermi Dirac, this is the Fermi Dirac distribution for a given energy. depending on K and sigma. And the chemical potential, which now is the Fermi level, because the chemical potential at temperature T equal to 0 is the Fermi level, okay? Well, now we need to replace the summation over K and spin by a factor of 2, because this is for spins, spin degeneracy, for spin 1/2, okay? So for spin 1/2, you have a factor of 2 corresponding to the degeneracy of the system, and you replace the summation by an integral over d3k, and summation here is replaced by integral. This has a volume in k space, so we need to correct that by the slightest, the lowest, the smallest delta k possible cubed, okay? Because you need to multiply here the summation by a delta k x, delta k y, and delta kz, and then you need to normalize properly. So this corresponds to the volume of the sample in the denominator in k space, their volume in the real space, and the 2 pi cubed, because the smallest delta k is 2 pi over L, which, if you consider a cubic volume, L is the dimension of the cube. The smallest wave number is 2 pi over L. You need to cube that, all right? So L cubed is the volume of the sample. So if you divide it by this delta K cube, you'll find the factor of volume divided by 2 pi cubed here, okay? So this is it. You replace the summation by integrals and summation over spin by a factor of 2, because you are considering no magnetic fields, no spin orbit couplings, and therefore the spin is a correction. So energies are independent of spin. You are replacing the energy by something which is independent of spin, and therefore you'll find out a factor of degeneracy when summing over spins. Okay, factor of 2 for spin half. If you have a particle of spin 3/2, the degeneracy factor here is a 4, and the degeneracy factor here corresponds to twice the spin of the particle plus 1. Okay, so for spin 1/2, you have 2 times 1/2 plus 1, which is 2. 3/2, we have 4. 5/2, you would have a 6, and so on and so forth. Okay, so now we need to calculate this object here. We need to calculate this integral. Okay, so but now we are considering the temperature T equals to 0, and therefore the number on the average, let us call it just the capital N here, is equal to twice the volume divided by 2 pi cubed, and integral over d3k over the entire k space, the Fermi Dirac function as a function of the energy and spin, but spins for now are neglected. Okay, so this is the Fermi Dirac distribution. Now, if you remember, the d3k is for a spherically symmetric problem. So spherically symmetric. Will be represented in spherical coordinates. So you would have a k squared d sine of theta, dk, d theta, d phi, but integrating over sine of theta, because this function has no, remember, E of K and sigma in this case is just h bar over 2m square m effective mass times K squared. Sorry. This defines a sphere in K space. So Kx, Ky, Kz for a given energy. That function is just a sphere with radius k. Okay, and the radius of a given for a given energy, the radius of the sphere. Just remember, k squared is kx squared plus ky squared plus kz squared. These are the three components of the wave vector or the momentum in proper units. It is equal to the twice the effective mass divided by the h bar squared times the energy. So for a given energy, you have a spherical surface of radius k, all right? Because this is a spherical, this is the equation for a sphere of radius twice the mass divided by h bar squared times the energy, okay? So this integration over all the theta phi, it is an integral over theta from 0 to pi and phi from 0 to 2 pi. This corresponds to a 4 pi factor. And therefore, this d3k here in 3 dimensions can be replaced by 4 pi k squared dk. You already integrated sine of theta, d theta, d phi. Okay? For a given vector here in the reciprocal space, you have a theta measured by, with respect to the kz axis and the phi measured with respect to the kx axis. So this is the conversion of this integral to spherical coordinates. It is because the energy has a spherical symmetry, all right? The energy has this symmetry. So it is better to integrate with respect to spherical coordinates in the K space, right? So let us replace that by this fact here. So remember d3k, let me write it here just to remember, 4 pi k squared dk, right? And now what we can do, we can just write the capital N, which is the total number of particles in the volume of the system, is twice the volume, 2 pi cubed. 4 pi comes from this, an integral over k squared dk, and the Fermi Dirac function depending on the energy, which depends on k, and the spin, it is independent on spin because we are already taking into account the factor of 2 here, so the spin is now omitted, okay? And this here, the twice times the volume, or the volume I'll let it here, the factor twice times 4 pi, this twice comes from spin, this is spin degeneracy, times 4 pi, 2 pi cubed here, k squared dk can be written as some density of states over the energy times the differential over energy. And this G here, in some places, is using the letter capital D, but this G I am using here is just to remember it's the density of states, the total density of states divided by a volume. Okay, so I am not taking into account this volume. This volume I will let it be explicitly represented here. So the density of states of the previous lecture divided by the volume is this G, this G factor here, which is the density of states. Density of states. It is measured in electron volts, if you are using electron volts, in electron volts, or sorry, in states per electron volts per cubic meter in the international system. Okay, well, electron volts is not international system, but I am using states per volume per electron volt here, right? And therefore, as you can see, this k squared decay can be replaced by, notice, twice the mass divided by h bar squared times the energy, because k squared is twice the mass divided by h bar squared energy. And dk, remember, if you take the differential of the energy, you have h bar squared over 2 times the mass k dk, but if you differentiate with respect to k here, you get a factor of 2. So let me just consider this factor here and use a 2 factor here. So 2 times k dk times this constant here is the differential over the energy. So dk needs to be replaced by dE, which is the differential of the energy, divided by h bar squared over twice the mass, the effective mass, times a factor of 2, which comes from the derivative here. I am using differentials here, so I must differentiate the energy with respect to k to find out what is the differential over the energy. And now I am just replacing this dk here by dk over dE times dE. This is what I'm calculating here. Okay, 2 times k, and k, we already know it is 2 times mass, effective mass, divided by the h bar square times the energy, and you need to take the square root here. So in this case, we have 2 times 4 pi, which produces an 8, which is equal to the factor 2 here, cubed is 8, and the pi cubed, and we have a pi in the numerator, so we have a pi squared, okay? K squared dk, it is that factor when we replace the k appearing here by its relation with energy. So of course, you will produce the square root of energy here, and the factor, this factor of 2 comes into play here, a factor of 1. And if you calculate all these mass and h bar factors here, you'll find out a total factor of twice the mass divided by the h bar squared to the 3 halves. Okay, if I properly address the constant here, because this here will become divided by this factor divided by that will become this factor squared, but you need to subtract 1/2 coming from this here. So you have a 3 halves here. Okay, so this is the density of states. Just keep that in mind. This is the density of states times the, okay, times the. So the G of E is equal to 1 over 2 pi squared twice the mass, the effective mass, of course, over h bar squared to 3 halves square root of energy, right? Keep that in mind. And now we can get rid of this factor of 2, 4 pi, and all that. What is left? total number of particles is just volume times G of E, F of E, and the Fermi level, dE. All right, this is what is left in this calculation. But now we have the total number of particles is volume. The whole problem here is these factors here are just constants, and we have 2 pi squared twice the mass over h bar squared, the effective mass to the 3 halves. We can put outside of the integration sign, and we have an integral from 0 to infinity at first, because this form of the density of states implies the energy starts from 0. You cannot have negative energies for a free electron gas with no additional interactions. Okay? If you plug in the magnetic field, you can have a potential energy, but here is just a kinetic term. Kinetic terms only allowed values are positive, so you have to integrate from 0 to infinity of this square root of E times the Fermi-Dirac distribution of, depending on E and the Fermi level, dE. But now, just remember, this is a step-like at temperature equal to 0. So in this case, what you have, a total number is equal to the volume times the constant, 2 pi squared, only pi is squared, and this factor, which is repetitive, it appears quite frequently. And now, if we take into consideration this Fermi-Dirac function is a step-like, it goes from 0 to the Fermi level with a 1, and from the Fermi level and beyond with zeros. It limits the integral from 0 to the Fermi level here of the square root of the energy integrated over the energy, over the integration variable energy. And remember, integrals of e to the some factor m here, or kappa perhaps, I don't know what to use here as a symbol. Suppose alpha here, integration of this corresponds to e to the alpha divided by alpha plus 1. Okay, so this form of integrals we already know how to calculate. To alpha plus 1, of course, divided by alpha plus 1. And in this case, we have provided a definition. The density of states depending on the energies, some d0, okay, d0 or g0 times the square root of energy, where g0 is 1 over 2 pi squared, 2 times mass divided by h bar squared to the 3 halves. This we call the g0 here, will produce a total number of particles equal to volume times this factor here, which appears here. The energy will be, the alpha will be 1/2. 1/2 plus 1 is 3 halves. Evaluated in the inferior limit, in the lower bound here in this integral, it produces 0. In the superior or the upper limit, it produces the replacement of the energy by the Fermi level to the 3 halves, divided here by 3 halves, which produces a factor of 2/3. So the energy is this. The calculation of the number, total number of particles, is this total number of particles. Okay. And now, if you divide it by the volume, you have a relation with the particle density. In this case, it's the electron density in the gas. Okay? It is just this n in electrons per cubic meter is just the total number divided by the volume in electrons by cubic meter if we are interested in electrons. And this produces the following result: 2/3 G0, which is this constant here, this constant, 1/2 pi squared, and the 3/2 of 2 times the mass elevated to 3/2, 2 times the mass, the effective mass divided by h bar squared. Okay, and the Fermi level to the 3/2. Okay, so let us see if this makes any sense. Okay, let us see if this makes any sense. Keep that in mind. Okay, so G0, just for us to remember, is 1/2 pi squared, 2 times the effective mass divided by h bar squared, elevated to 3/2, to the 3/2. Okay, well, if we have in K space a sphere, the maximum radius of the sphere is the Fermi wave number. So this is the Fermi energy, Fermi level can be related to the Fermi wave number. Fermi wavelength, and K of Fermi is 2 pi over the Fermi wavelength of the material. You can relate this energy to a temperature. So Fermi temperature is the Fermi level divided by Boltzmann's constant. This is the Fermi temperature. In Kelvin, okay, it's absolute value. And Fermi wavelength is just related to the wave number. And the wave number is related to this relation here. Okay, this is another possibility of defining Fermi energy. Okay, so what is the volume of this sphere here? What is the volume of this sphere? Volume in K space corresponds to 4 pi over 3, the Fermi wave number cubed. Okay, because this is the total volume of the Fermi sphere. This is the Fermi sphere. The total volume is just 4 pi divided by 3. This is the volume of a sphere. Okay, so what is the number of particles we can put inside the Fermi sphere? How many particles there are here? Because each particle can occupy only 1 K inside the Fermi sphere. So how many electrons in this case? How many electrons? Well, an easy calculation corresponds to total number of electrons inside the Fermi sphere, corresponds to volume of the Fermi sphere divided by the infinitesimal volume of one given K, which is delta K cubed, and with the factor of 2 because the spin degeneracy. Spin degeneracy. Okay? At each given K, I can put 2 electrons with distinct spins, one up and one down. This is the origin of this spin degeneracy factor here. If we multiply the volume of the sphere in K space by 2, because at each point inside the Fermi sphere I can put 2 electrons, and divide it by the slightest volume, the smallest volume in the K space, which contains only one point in the K space. This is Kx, Ky, and Kz. I'll find out the total number of particles inside the Fermi sphere. And this produces the following: 2 times 4 pi divided by 3, the Fermi K, or the Fermi wave number, sorry, divided by 2 pi cubed over the volume, because delta Q to the cube corresponds to 2 pi to the cube divided by Lx times Ly times Lz. If you construct a solid with the 3 dimensions to be equal, you have L cubed, but this is just the volume in general, in the real space. Therefore, you have N equals to the factor of 8, which cancels this 2 pi cubed here. This the factor of 2 here, cubed is 8. A factor of pi cancels 1 here, so I have a Fermi K, a Fermi wave number cubed times the volume divided by 3 pi squared. And therefore, we find that the Fermi wave number is related, if you divide everything by the volume, the Fermi is related to the density of the gas by 3 pi squared, the density of particles in the gas to the 1/3. Okay, to the 1/3. Or, of course, you can relate the other way. Of course, you can relate the other way. You can write that N is equal to Fermi wave number divided by 3 pi squared. Now, if you insert the Fermi K, replacing it by the energy relation, you'll find out 1 over 3 pi squared, 2 times the effective mass divided by h bar squared. I am just taking the square root of this equation here to find out what is K of Fermi, or the wave number at the Fermi level. And we will have the square root of that factor, but we need to cube that, so it's elevated to 3/2. And the energy, which for the K of Fermi is square root also, we need to elevate it to put in a power of 3. So we have 3/2 here. But notice that this is 2/3. This factor here is 2/3 of G0. Okay? So that's all right. You can calculate the Fermi level considering the density of the Fermi gas. If you plug in some values for densities around 10 to the 27 to 10 to the 29 particles per cubic meter, okay, or cubic meter to the -3, you'll find out, you can calculate the Fermi wave number, and you can calculate the Fermi level. Just if you calculate this, you can plug in there and you'll find out that the Fermi level for metals, this is for metals, you'll find out is around a few electron volts to tens of electron volts. You can find these numbers, right? For sodium, I guess the value is 3.2 electron volts. Okay, this is the Fermi level calculated taking into consideration the electron density of the gas. Now we can calculate the energy. So the Hamiltonian average is the energy of the gas. This is the energy of the gas, the total energy. Okay? The total energy of the gas, and it can be calculated in the following way. We pick up the average of the Hamiltonian corresponds to summation over K and spins, the energy depending on K and spins, times the average of the number operator for each K and each spin, which is just, again, the Fermi-Dirac distribution. And therefore, at temperature equals to 0 and magnetic field equals to 0, we can replace this total energy of the Fermi gas by an integral volume here, because every time we replace a summation over K and sigma by an integral over dE times G of E, every time we replace a summation by an integral over d3k volume 2 pi to the cube 2 times, because summation over spins, we can replace it directly by a volume times the integral over the energies of the density of states, G of E. And therefore, when we replace this summation here by the integral over d3k, is just the same as performing an integral from 0 to infinity, in general from minus infinity, because I don't know exactly what this is. In a general case, I don't know if negative energies are allowed. So in general, you need to integrate from minus infinity to infinity. Okay. And the energy value here, which is all the dependence on K is connected to the proper value of the energy. We replace the integration over K by integration over energy. G of E times the Fermi Dirac, which depends in this case on the energy and the Fermi level, times dE. So this is the total energy of your system. Okay, this is the total energy of your system. And this is easy to perform because this G of E is just that constant G0, square root of the energy. It's just better to use this G0 because you don't want to keep using that 2 times mass divided by h bar squared to the 3 halves. And this is just a burden to carry over calculations. So we just define a constant G0 there. And you'll find out that the total energy of your electron gas will be volume times G0, because the G0 comes from this G, which is a constant of integration, and integral from minus infinity to infinity because of this square root here from 0 to infinity. But because of this Fermi Dirac distribution at temperature T equals to 0, it finishes at the Fermi level. So we integrate to the Fermi level. Energy times the square root of energy, you find a factor of 3 halves here, and you need to integrate over the energy. This is easy to perform. So if you divide the energy by the volume, you have the energy density of your gas. It is G0, okay? If you integrate the 3/2, you have a Fermi to the 5/2 divided by a factor of 5/2. So 2/5 of that, I guess, if it's properly calculated. And, and therefore, just remember that the density of particles, which corresponds to the N over V, corresponds to 2/3 of G0, the Fermi energy to the 3/2. Okay, so this is the two results we have found so far. Okay, so the two results we have found. If you want to calculate the mean energy per particle, you divide the total energy by the total number of particles, and you'll find out, you can multiply both sides by the volume, and you have this factor here divided by that factor. You'll find out a factor of 3/5 of a Fermi energy, because if you divide this by that, you'll find 5/2 minus 3/2, which is just 1, a factor of 1. Notice that the G0 cancel out, and 2/5 divided by 2/2, it's 3/5. Okay, so each particle on the average has an energy of 3/5 of the Fermi level. Okay, this is the result of a Fermi gas. This is the result for a Fermi gas. Okay, now we need to perform calculations with respect to the distinct temperatures, not only at zero. Okay, so if we want to calculate for non-vanishing temperatures, for temperatures distinct from zero, what you need to do? Well, you need to calculate Fermi integrals of the following form, from minus infinity to infinity, of some integrand depending on the energy. It's typically written as in the following way, times the Fermi Dirac distribution, but here comes temperature. Okay, so temperature enters via the reciprocal of the temperature, this beta constant here. Okay, and you need to perform this type of integrals, and this is very difficult because now this exponential depends on the temperature, is not step-like anymore, and there is a way to deal with it to many orders of magnitude, but we will stop at the temperature squared. So what you do is something called the Sommerfeld expansion. Okay, Sommerfeld expansion. For integrals of that form, you can perform some tricks to do that integrals, and you have from minus infinity to the chemical potential, you just integrate this integrand here. So this is the Sommerfeld expansion, plus pi squared divided by 6 by a factor of 6, 1 over beta squared, but this is just the kBt squared, so it's temperature squared in the end, the derivative of the function, which is usually denoted by h primed, but corresponds to the derivative with respect to energy, okay, evaluated at the chemical potential, okay, so evaluated at the chemical potential, so h prime of mu is just the derivative evaluated at the chemical potential, and plus orders of temperature to the fourth power, okay. So if you want to go to the second order in the temperature in a series of perturbative terms, the Sommerfeld expansion, you can find what it is in a complete sense, but usually you go to the second order in the temperature, so you have a zero order, a second order, a fourth order, a sixth order. It goes like 1 over beta squared, 1 over beta to the fourth. And if you are not going to the Fermi temperatures, if you calculate for a metal Fermi temperatures, go to thousands of Kelvin. If you are dealing with room temperature, it is a good approximation to stop at the second order of the temperature, okay? Because for metals, the Fermi temperature, which is the Fermi energy divided by Boltzmann constant, it is in the range of 5,000, 10,000 kelvins, okay? So you just is uh, justified to stop at second order in the 1 over beta, because beta for small temperatures, okay, so for 1 over beta for small temperatures is just the temperature, and you can use this fact here. So small variations over the Fermi level here for temperature, the Fermi Dirac fluctuates here near the Fermi energy, and this here is dependent on kBt, but this region which has a dimension of kBt is very small compared to the kb, the Fermi temperature, okay. So it's a good approximation to go to second order in temperature. All right. So let us calculate a few things first, using, of course, the Sommerfeld expansion. And the first of them is the chemical potential. It will be corrected to second order in temperature. Remember, at T equal to 0, it is exactly equal to the Fermi level. So it is an expansion around the Fermi level. But remember, if you calculate the number of particles in the system, if the system is closed, it is independent of temperature. Okay? The total number of electrons in your system, if your system is closed, it is independent of the temperature of the system. And therefore, you can calculate in the following way. It is an integral from minus infinity to infinity, the density of states times the Fermi-Dirac distribution of the chemical potential times dE. And now we can use, remember the Fermi-Dirac is just that 1 over exponential of beta E minus mu plus 1. Here, this is just the problem where we want to use the Sommerfeld expansion. So we go from minus infinity to the chemical potential here, G of E times dE plus the integrand here, which is just the density of states, pi squared over 6 kb squared, temperature squared, because it's inverse of beta squared, okay, and G prime calculated at the chemical potential here. This is it, okay. This number must agree with 2/3 of G0, the Fermi energy to the 3/2, because this is the value, okay, times the volume here, times the volume, okay. This is the value of the total number of particles in the system, okay. And now we perform a trick here, because from minus infinity to the Fermi level, G of E integrated over dE, it is already the total number of particles, which is corresponding to the zero temperature, the absolute zero. And now we integrate this part here from the Fermi level to the chemical potential, G of E dE, plus that other factor there, pi squared over 6 kBt squared, G prime calculated at me, at the chemical potential. And this thing here must be exactly zero, because otherwise the number of particles would change. Okay, it would change in in the sense that the system is a closed system. The number of particles is independent of the temperature, and this integral already produced the total number of particles in the system. So the other corrections, which depends on the chemical potential and the integral from the Fermi energy to the specific chemical potential at that temperature, plus the second order corrections with respect to temperature, it must vanish. Okay. Now we can integrate that. But since the Fermi uh, temperature is very high and the chemical potential is very close to the Fermi energy for small temperatures, we can just replace this integral by an approximation which corresponds to G calculated at the Fermi level times the integral from the Fermi energy to the chemical potential over dE, and this is approximated the chemical potential minus the Fermi energy, Fermi level, times the density of states. Here we have a volume, of course, volume, volume, volume. Okay, so volume here, volume here, volume here, because V times this density is what produces the total number of particles. Okay, so this integral here we approximate, and therefore the chemical potential minus the Fermi energy times the Fermi density, the density of states at the Fermi level, the volume cancel out from here and here, so I can neglect that. It must be equal to minus pi squared divided by 6 k squared t squared. This G prime here, I can replace the chemical potential here by around the Fermi level. So G prime at the Fermi level here is the first order approximation, because any temperature dependence on the chemical potential will produce higher orders in the temperature. So this G prime here we will replace by, instead of calculating at the chemical potential, we calculate it at the Fermi energy, Fermi level, sorry. In this way, we have the chemical potential is equal to the Fermi level minus pi squared over 6 kb squared t squared g prime divided by g calculated at Fermi level. But just notice that g prime, g over e is as a function of e is equal to the g0 times the square root of the energy. If you calculate the derivative, you find out a g of e primed is equal to the g0 1/2 square root of the energy. Okay, this is the derivative. So if you insert that into the calculations, notice that the G0 constant cancel out. You will have a factor of 1/2, and the square root of the energy at the Fermi level multiplies the square root of the energy here. So we will have something like approximately given by the Fermi level times, if you put the Fermi level into evidence, 1 minus pi squared Boltzmann constant squared, temperature squared, divided by Fermi level squared, and the factor of 12 here. Okay, because 1/2 times 1/6 it produces that, and therefore, remember the Fermi energy when related to the Fermi temperature, you have thousands of kelvins. This energy corresponds to thousands of kelvins. So for a few kelvins of hundreds of kelvins, the corrections to the chemical potential are very soft. You don't have very large, you don't have a huge correction. So the second order in temperature is pretty fine if you want to make calculations in room temperature. Okay, so you have Fermi energy here, 1 minus pi squared over 12, and if you write this as kb squared times the Fermi temperature, you have temperature divided by Fermi temperature squared. This is the chemical potential plus orders of the fourth power of the temperature. Okay, this is the changing in the chemical potential due to temperature. It slows, it lowers, it lowers by a factor depending on the square of the temperature. So chemical potential, if you plot against the temperature, you have the Fermi level here, and this decreases as a square of the temperature. It is it is a it is understandable because of the following fact. At zero, Fermi Dirac distribution is step-like, and the chemical potential is related to putting one more particles into the system. And for temperature increasing, the Fermi distribution gets smeared around the Fermi energy. So you can, since the particles here came here, you can insert with a certain probability a particle at a lower energy than the Fermi level. For temperature equal to zero, if you want to insert one more particle in the system, certainly it must be a particle with energy higher than the Fermi energy. But now you have states unoccupied with a certain probability below the Fermi energy. So the chemical potential is reduced by the effect of temperature, because some energy states are depleted here below the Fermi energy at zero, uh, because these particles are promoted by temperature. Okay, but this is it for the chemical potential. Now we can calculate the specific heat okay, specific heat corresponds at a constant volume, the derivative of the total energy with respect to temperature, and you divide it by the volume of the system. Okay, so now you need to calculate the total energy as a function of the temperature, and the total energy of your system corresponds to a, a volume times density of states here times energy times Fermi Dirac distribution as a function of energy and chemical potential. Temperature enters here over dE from minus infinity to infinity. And now you can again use the Sommerfeld expansion, okay? And for that, you have volume here, an integral from minus infinity to the chemical potential of this integrand here plus pi squared divided by 6 kBT squared, an integral of, a derivative of this thing here, evaluated, so we primed here, evaluated at the chemical potential, which depends on temperature. Here you already have a dependence on temperature, but at least you will find that the energy corresponds to some E0. Okay, I'm not going to details, a very detailed calculation you can find out, but you'll find corrections with something like some constant here, a kBT squared times temperature squared. Because if you go to second order in temperature, what you can find out is a second order of the temperature. You cannot have fourth orders of higher order because you are truncating your problem here. And therefore, if you perform a calculation over the specific heat, remember this total energy is multiplication by the volume. So if you divide by volume, and this constant here also will have a volume here. So if you divide by volume and calculate the derivative over temperature, you'll find out that the specific heat will be a constant A times Boltzmann's constant squared times T, twice that constant to be precise. The constant comes from the precise calculations. It depends on the density of states at the Fermi level, okay? But it is dependent on the temperature, linearly dependent on temperature. It is for a Fermi gas. Fermi gas at small temperatures. Okay? For sometimes, for a very long time, perhaps, they thought that the contribution of the electronic gas in a metal to the specific heat was the most important contribution because electrons contribute mostly to the conductivity of the material. But if you calculate here, you'll find a very weak dependence. Remember, for a um, ideal gas, a specific heat for ideal gas goes like the density of particles times kb, okay, and is nearly independent of the temperature for an ideal gas. But here you find out it is a linearly dependent on temperature, and this constant here is depends on the Fermi temperature, which is thousands of Kelvin. Okay, so the specific heat contribution or the contribution of the electron gas to the specific heat of a material is neglectful at higher temperatures because there are other more important contributions to the specific heat. The main contribution comes from the phonon gas, the lattice vibrations of the solid. Okay, but this is the calculation. It produces a factor of T, and the next order contribution will go like B T to the third power, okay? Because a correction of the energy will produce a order of temperature to the fourth power. If you calculate the derivative, you'll find out a factor of, it's not magnetic field, okay? The constant, let me put a B1 here, T to the cube, okay? So this is the exact or the form of the contribution of the electron gas to the specific heat of a material. It depends linearly for small temperatures. If you go to higher temperatures, it gets a correction to the T cubed, but it is the main contribution comes from the phonon gas, so the electron contributions perhaps are less important at higher temperatures. And compared to the what one expect from ideal gas, you find out that is orders of magnitude less than expected for an ideal classical gas. To finish, magnetization and electronic properties. Magnetization and electronic properties of the Fermi gas I will discuss in the next lecture, because I guess this lecture is it's it's more heavy than I thought it would be. So let us discuss magnetization and properties of transport for the Fermi gas, the electron Fermi gas, in the next lecture. Hope you appreciate it, and find out more for the Sommerfeld expansion, and find out as an exercise, find A in CV. Okay, find a constant. We found that it is a constant A kb squared times temperature, something like that, a factor of 2 because of the derivative. But it doesn't matter. It's just a constant here. Try to calculate using the Sommerfeld expansion. You can exactly provide the value for this number here. In the next lecture, we will discuss magnetization and electronic properties of the Fermi gas. Okay, bye bye.